You know, we encounter mixtures every single day, everywhere we look, really. I mean, think about it. A brass doorknob,
Yeah,
the fizz in your soda, even our own bloodstreams, right? They all depend on mixtures.
absolutely.
But today we are diving deep, going all the way in on one very specific type of mixture, solutions. Now, I know what you're thinking. Solutions. Sounds kind of boring, maybe a little too textbooky.
Yeah, you might be thinking back to like high school chem class.
Exactly.
Yeah.
But trust me, there is so much cool stuff going on when we talk about how things dissolve and how they interact. It's honestly way more fascinating than you might think.
I mean, we really went through a bunch of material to really figure out what is at the heart of solutions.
Hmm.
And our goal today is to just pull out those key insights, really understand how solutions form, the unique properties they have, and ultimately, like, why should we care?
Yeah, why does it matter?
Yeah.
Okay, so let's start with the absolute basics. What actually is a solution?
Well, at its very core, a solution is a homogeneous mixture. Yeah. So picture this. You're stirring salt into water. It disappears.
Right.
That's what we call a solution because it looks completely the same throughout. Now, within this solution, we have two key players, the solvent and the solute.
Right.
The solvent is typically the component that's present in a larger amount, and it actually determines whether the solution is a liquid, a gas, or even a solid. In our saltwater example, water is the solvent.
Okay, so the solvent is like the big boss.
Exactly.
That's calling the shots.
Exactly. And then we have the solute,
Right.
which is the substance that dissolves. So in our case, that would be the salt.
Okay.
But here's what I find really cool is that there's this amazing diversity of solutions that can exist depending on whether the solute and the solvent are gases, liquids, or solids. Like think about the air we breathe.
Oh, yeah, good point.
It's actually a gaseous solution, oxygen mixed into nitrogen.
Wow, I never thought of it that way.
Yeah, it's pretty neat.
So we tend to think, I think, a lot about liquids, right, when we talk about solutions.
Yeah.
Like if you have a gas dissolved in a liquid, maybe like that smell of chloroform you might find in a lab setting, that would be mixed with nitrogen.
Yeah.
Or like when you mix ethanol and water to make,
Mhm.
well, not that we'd advocate that, but they blend perfectly. Or the classic example of a solid in a liquid, like when you're stirring sugar into your coffee.
Right.
But it doesn't stop at liquids, does it?
No, it doesn't. We also have something called solid solutions.
Solid solutions. Okay.
Which I know it sounds a bit weird. But imagine this. Hydrogen gas, which is obviously a gas, can actually get trapped within the structure of a metal like palladium.
Really?
That's a gas in a solid solution.
Mm.
Or think about liquid mercury. It can be mixed with solid sodium to form something called an amalgam,
An amalgam.
like a sodium amalgam. And then you have, I mean, even solid solutions are possible. Like if you were to melt copper and gold together and let them solidify, you get a solid alloy, a uniform mixture of those two metals.
Mm.
It just goes to show how this idea of a solution, it's really versatile.
Yeah, it pops up everywhere.
It does.
Okay, so we know what a solution is, at least in a basic sense. But then how do we actually describe what's in these solutions?
Right.
Saying, you know, there's a little bit of this or a lot of that doesn't really cut it in science, does it?
No, no.
Especially in chemistry.
So how do we get specific?
That's where this idea of concentration comes into play. We need a way to express exactly how much solute is present in the solvent.
Mhm.
You need those numbers.
Right.
And our sources detail several different ways that we can do this. So let's go through some of those.
Yeah, let's break it down.
The first one is mass percentage. Think of it like a recipe.
Yeah.
You're baking a cake, and the recipe says it's 10% sugar by mass.
Okay.
That means for every 100 grams of cake batter, 10 grams of that is sugar.
Gotcha.
It's the same principle with solutions. So a 10% glucose solution means that for every 100 grams of the total solution, 10 grams of that is glucose.
Okay, so it's like the proportion?
Exactly.
Yeah.
And this method is actually widely used in various industries, like that commercial bleach you might have under your sink.
Yeah.
That's around 3.62% sodium hypochlorite by mass.
Interesting.
Then we have volume percentage, which is a very similar concept, but instead of using mass, we're using volumes. So if you have a 10% ethanol solution, it means that for every 100 milliliters of the solution, 10 milliliters of that is pure ethanol.
Okay.
And this is really handy when you're dealing with, well, mixing liquids. Like, for example, the antifreeze in your car.
Ah, yeah.
Often a 35% ethylene glycol solution by volume. And that actually helps lower the freezing point significantly, which, prevents your engine from Well, freezing up in the winter.
Right. Super important.
Very important.
Right.
Now, sometimes you'll come across something called mass by volume percentage.
Mass by volume.
This is often used in medicine and pharmacy, and this refers to the mass of the solute in grams that's dissolved in every 100 milliliters of the solution.
Okay.
But then, sometimes we're dealing with really, really tiny amounts of something dissolved in a solution,
Right.
like pollutants in water or even in the air.
Yeah.
And in those cases, we use parts per million, or ppm. Imagine finding like 5.8 molecules of oxygen for every million molecules of seawater.
Wow.
That gives you an idea of just how small a concentration 5.8 ppm really is.
Yeah, it's like the trace amount.
Exactly, the trace amounts.
Okay, so now for one that's maybe a bit more abstract, mole fraction,
Yes.
often represented by a little x. What is that all about?
So mole fraction, you can think of it as the share each component has in the total number of molecules present in the solution.
Oh, okay.
So if you have a solution with two components, the mole fraction of one plus the mole fraction of the other always adds up to 1, because it's like, the whole pie.
Makes sense.
And it's really useful when you're trying to understand things like vapor pressure and when you're working with mixtures of gases. Our sources have a good example, actually, where they calculate the mole fraction of ethylene glycol. It's one of those things that seeing it in action helps you really grasp it. Then we have molarity, often denoted by a capital M, which I'm sure is familiar from chemistry class.
Ah, yes.
Molarity is the number of moles of solute that are dissolved in 1 liter of the solution.
Odd solution.
So if you have a 0.25 med NOH solution,
Yep.
it means that there's a quarter of a mole of NaOH in every liter of that mixture.
Yeah.
Our sources have an example that walks you through how to calculate this, given the mass of the solute and the volume of the solution.
Okay, so that's molarity. And then last but not least, we have molality.
Molality, denoted by a lowercase m. And this one is a bit different because it's the number of moles of solute per kilogram of solvent, not the entire solution.
The solvent, okay.
So a 1.00 meto KCl solution means that you have 1 mole of potassium chloride dissolved in every kilogram of water, which is the solvent in this case. There's an example in our sources, actually, that shows how to calculate this for ethanoic acid in benzene, so you can kind of see it in action.
Yeah, examples are always helpful.
Always. Now, it's important to highlight a key difference here. Mass percentage, ppm, mole fraction, and molality. They all rely on mass, and mass doesn't change with temperature.
Right.
So these ways of expressing concentration, they're going to remain the same, even if the temperature of your solution fluctuates.
Okay.
But molarity, on the other hand, can change with temperature because the volume of a liquid, it expands or contracts as the temperature changes.
Ah, that makes sense.
And this is something that scientists need to take into account when they're doing very precise work.
Right. So we've got a handle on how to describe how much stuff is dissolved in these solutions.
Right.
But what makes something actually dissolve in the first place? Like, why does sugar just disappear in water, but it just sits there in oil?
Right.
Why is that?
That brings us to the concept of solubility.
Yep.
And our sources define it as the maximum amount of a particular solute that can dissolve in a specific amount of solvent at a given temperature.
Okay.
And the rule of thumb here often is like dissolves like.
Like dissolves
But-
like.
Yeah. So polar substances, think of them as molecules with a positive and a negative end, kind of like a tiny magnet.
Got it.
Things like water and sugar, they're polar, and they tend to dissolve each other because those electrical attractions, they're compatible.
Okay.
Now, non-polar substances, they don't have those charges. Things like oil and grease, they're non-polar. So they tend to dissolve in other non-polar substances. If you've ever tried to mix, say, salt, which is polar, with oil, which is non-polar,
Right.
or if you try to mix something like naphthalene, which is a non-polar solid, with water,
Yeah.
they just don't mix well. It's all about those intermolecular forces, those little attractions happening between
They've
molecules.
got to be compatible.
Exactly. They need to be compatible.
They need to get along.
They do. Our sources also delve into this concept of a dynamic equilibrium that occurs when a solid dissolves in a liquid. So initially, the solid breaks apart and the particles spread into the liquid.
Yay.
That's dissolution.
Dissolution.
But as more and more of it dissolves, some of those dissolved particles, they kind of bump into the undissolved solid
Yeah.
and they stick back onto it.
Okay.
That's what we call crystallization.
Audicylization.
And at a certain point, those two processes, they reach a balance.
Gotcha.
And when that balance is reached, we have what's called a saturated solution. That means it's holding the absolute maximum amount of solute that it can at that specific temperature. And no more will dissolve, no matter how much you stir or shake it.
It's full.
It's full.
Yeah.
But if you haven't reached that point yet, we call that an unsaturated solution, which means you can still add more solute and it would continue to dissolve.
It's got room.
Yeah.
Okay. So now that we understand that, what are the things that we can do to actually change how much of something dissolves?
Well, temperature plays a significant role, particularly for solids dissolving in liquids. And our material links this back to Le Chatelier's principle. If the process of dissolving a solid absorbs heat, so it's endothermic,
Endothermic.
then heating up the solution will typically allow more of it to dissolve. Think about trying to dissolve sugar in your tea. You could dissolve a lot more sugar in hot tea compared to cold tea.
Oh, yeah. Good point.
Right.
Yeah.
But if dissolving a substance actually releases heat, if it's an exothermic process, then increasing the temperature might actually cause less of it to dissolve.
Oh, interesting. It's the opposite.
Yeah. Now, interestingly, pressure doesn't really have a noticeable effect on the solubility of solids or liquids in liquids.
Okay.
They're just not very compressible. So you can squeeze them all you want. It's not going to force more certainty to dissolve.
But it's a whole different story when we talk about gases dissolving in liquids, right?
Completely different ballgame.
Yeah.
Because both pressure and temperature, they play a huge role. Think about how only a small amount of oxygen dissolves in water, but it's just enough to support aquatic life.
Yeah.
But then you have gases like hydrogen chloride, HCl, which are incredibly soluble in water. And this is where Henry's law comes in. It helps us quantify this relationship.
Okay, so tell me about Henry's law.
Basically, it states that at a constant temperature, the amount of a given gas that dissolves in a liquid is directly proportional to the partial pressure of that gas above the liquid.
Okay, so if there's more pressure.
Exactly. So if you increase the pressure of the gas, more of it will dissolve into the liquid. Our sources include a nice figure, actually, that illustrates this relationship.
It's really interesting to me how different gases have different, what they call Henry's law constants.
Well,
It's
yeah.
like each gas has its own little quirks when it comes to dissolving.
They really do, yeah.
Mm.
A higher constant means that less of the gas will dissolve at a given pressure.
Oh, okay.
And for gases like nitrogen and oxygen, those constants actually increase with temperature.
Oh, really?
Yeah, and that actually explains why fish prefer colder waters. Colder water can hold more dissolved oxygen because those constants are lower.
Huh, that's cool.
Yeah, and there were actually a lot of practical applications of Henry's law.
Mm-hmm.
Think about your favorite carbonated drink. Those are bottled under high pressure to force a lot of carbon dioxide to dissolve in the liquid.
Hmm.
When you open the bottle, you release the pressure, and suddenly the gas becomes less soluble, so you get all those bubbles.
Ah, makes sense.
Then there's scuba diving. When a diver goes deep underwater, the increased pressure forces more nitrogen from the air in their tank to dissolve in their blood.
Oh, wow.
Now, if they come up too quickly, that dissolved nitrogen can form bubbles. That can be really painful and dangerous. It's called the bends.
Yeah, the bends. I've heard of that.
That's one reason why divers use mixtures that include helium, because it's much less soluble in the blood. And consider what happens when you go up to a really high altitude. The lower partial pressure of oxygen at those heights means less oxygen can dissolve into your blood. And that's a contributing factor to altitude sickness. Our sources even go through a sample calculation showing how much nitrogen can actually dissolve in water at a given pressure.
So it's not just theoretical.
No, it's very real-world stuff.
Let's move on now to something a bit more subtle. Vapor pressure of liquid solutions.
Okay. But first, maybe just a quick reminder, what is vapor pressure?
So imagine you have a sealed container with water in it.
Okay.
Some of those water molecules, they're going to have enough energy to escape the liquid phase and become a gas.
Right.
And those gas molecules, they'll exert a pressure, and that's what we call vapor pressure.
Okay.
And eventually, the system reaches an equilibrium where the rate of evaporation is equal to the rate of condensation.
Right.
Now, the question is, what happens if we have a solution of two volatile liquids? In other words, liquids that evaporate easily.
Okay.
Well, they're both going to contribute to the vapor pressure above the solution.
Gotcha.
And a chemist by the name of Raoult, he actually came up with a law to describe this behavior. It's called Raoult's law. And basically it states that the partial vapor pressure of each liquid in the solution is directly proportional to its mole fraction in the solution.
So if a liquid makes up, say, 70% of the molecules, it's going to contribute 70% of the vapor pressure.
Pretty much.
Now, we also need to consider Dalton's law of partial pressures, which tells us that the total pressure above the solution is simply the sum of the partial pressures of each of the components.
Right.
So if we combine Raoult's law and Dalton's law, we end up with an equation that tells us that the total vapor pressure above the solution It all boils down to how much each component is in the liquid and what their individual vapor pressures are when they're pure.
So it depends on what they're mixed with.
It does. And if you plot it out, it turns out to be a linear relationship when you graph it against the mole fraction of one of the components.
Mm.
Our sources actually have a nice visual showing this.
Cool.
And then we can even figure out what the composition of the vapor itself is, what percentage of each liquid.
How do we do that?
Well, using Dalton's law again, we can see that the proportion of each component in the vapor phase is directly related to its partial pressure above the solution.
Right.
And actually, the sources have a worked example with chloroform and dichloromethane, and it demonstrates how the vapor above the solution tends to be richer in the more volatile component, meaning the one with the higher pure vapor pressure,
Oh,
the one that evaporates more easily.
okay.
It's interesting. Raoult's law and Henry's law, they're actually related.
Oh,
Yeah. Remember, Henry's law was about the solubility of a gas in a liquid.
right.
Well, if you think about a solute that's really volatile, one that really wants to become a gas,
Okay.
you can actually think of Raoult's law as just a specific case of Henry's law, where that Henry's law constant is simply the vapor pressure of the pure solute.
Huh. Cool.
So they're very much connected. Now, what happens if we dissolve a non-volatile solid, something that doesn't evaporate easily like salt or sugar, and we dissolve that in a volatile liquid like water?
Okay.
Well, in that case, only the water molecules can escape into the vapor phase.
Right, because the salt can't evaporate.
Exactly.
Huh.
And because the solute is kind of taking up some space at the surface of the liquid, fewer water molecules can escape. So the overall vapor pressure of the solution ends up being lower than that of pure water.
Makes sense.
And the key thing to remember here is that this lowering of vapor pressure, it just depends on how many solute particles are present, not on the specific nature of the solute particles themselves.
Okay.
So we can generalize and say that for any solution, the partial vapor pressure of a volatile component is proportional to its mole fraction in the liquid.
Okay.
And if you have a non-volatile solute in a volatile solvent, it boils down to the vapor pressure of the solvent being equal to its mole fraction times its pure vapor pressure.
Okay.
And again, our sources have a helpful diagram that shows this effect.
So now let's get into ideal solutions
Yes.
versus non-ideal solutions. What's the difference?
Well, not all solutions are created equal. Some solutions follow Raoult's law perfectly across all concentrations.
Like the well-behaved ones.
Exactly. We call those ideal solutions.
Okay.
But then many other solutions deviate from Raoult's law.
The rule breakers.
Right. And those are called non-ideal solutions.
Okay. So these ideal solutions, they obey Raoult's law across all concentrations.
Right.
And when you mix the components, there's no heat given off or absorbed, meaning zero enthalpy of mixing, and there's no change in volume, meaning zero volume of mixing.
Mm.
Now, on a molecular level, this means that the forces of attraction between the molecules of the two different components, what we call AB interactions, are just as strong as the forces between molecules of the same type, AA or BB interactions.
Great, Tasha.
So when you mix them together, it's like everyone is equally happy being next to each other. Mixtures of very similar substances like N-hexane and N-heptane, those tend to behave almost ideally.
Okay, so those are the goody two-shoes.
Exactly. Now, non-ideal solutions,
Right.
those are a different story. They don't follow Raoult's law, and their vapor pressures can either be higher or lower than predicted.
So unpredictable.
A bit more unpredictable, we talk about positive deviations where the vapor pressure is higher than we'd expect, and negative deviations where it's lower than we expect.
Higher or lower. Okay.
Right. So positive deviations typically happen when the forces between the different molecules, so those AB interactions, are weaker than the forces between like molecules, the AA or BB.
Okay.
So in that scenario, it's easier for molecules to escape into the vapor phase.
Yeah.
And that leads to a higher vapor pressure overall.
They're more likely to escape. Okay.
Yeah. One example is if you mix ethanol and acetone. Ethanol molecules love to form hydrogen bonds with each other.
Right.
But when you introduce acetone into the mix, it disrupts some of those hydrogen bonds.
It's getting in the way.
Exactly. So it actually makes it easier for ethanol to escape, to evaporate.
Gotcha.
Another example is carbon disulfide and acetone. That also shows a positive deviation.
Okay. What about negative deviations?
So those happen when the AB interactions between different molecule types are stronger than the interactions between, like, molecules.
So they're more attracted to the other type of molecule.
Exactly. So it's actually harder for them to escape into the vapor phase, resulting in a lower vapor pressure. A classic example of this is if you mix phenol and aniline. These molecules, they can form stronger hydrogen bonds with each other than they can with themselves.
Interesting.
So they kind of stick together more. Similarly, chloroform and acetone, they can actually form a hydrogen bond between each other. And that also leads to a negative deviation from Raoult's law. And then we have these really fascinating things called azeotropes.
Azeotropes.
Yeah.
Okay.
These are mixtures that actually have the same composition in both the liquid and the vapor phases when they boil.
So it's like they're inseparable.
Yeah. And because their vapor has the same proportions of components as the liquid, you can't separate them just by boiling and condensing.
So you can't separate them.
Right, like fractional distillation, that common separation technique, just won't work.
Interesting.
Now, there are two main types of azeotropes.
Okay.
We have minimum boiling azeotropes, which form in solutions that have large positive deviations from Raoult's law.
Okay.
Like, a classic example of this is the ethanol-water mixture you get from fermentation. You can distill it up to about 95% ethanol, but then it forms an azeotrope, and you just can't get pure ethanol by regular distillation methods.
Wow.
Then, on the other hand, we have maximum boiling azeotropes.
Okay.
These form in solutions that have large negative deviations. In these cases, the boiling point of the mixture is actually higher than the boiling point of either pure component.
Higher.
Yep. A good example of that is nitric acid and water.
Okay.
They form an azeotrope at about 68% nitric acid.
Okay, so now what about colligative properties? I always found this a really interesting aspect of solutions.
Colligative properties.
Yes.
Yes, these are super useful because they only depend on the number of solute particles in the solution, not on their identity.
Just the number, not what they are.
Right, like it doesn't matter if it's sugar, salt, or some other molecule.
Yeah.
And they all tie back to the idea that the vapor pressure is lowered when you add a solute.
Okay.
There are four main colligative properties that we look at. Relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure.
Okay, so let's talk about each of those.
All right, so the first one is relative lowering of vapor pressure.
Okay.
We already mentioned this, right? That adding a non-volatile solute decreases the solvent's vapor pressure.
Right.
Raoult's law gives us a way to quantify this. It says that the relative decrease in vapor pressure is actually equal to the mole fraction of the solute.
Okay.
And for dilute solutions, this can even be used to determine the molar mass of an unknown non-volatile solute. Our sources have a specific equation and even a worked example to show how that's done.
Oh, that's neat. So then what about elevation of boiling point?
So we know that the vapor pressure of a solution is lower than the pure solvent, right? That means we have to heat it up to a higher temperature to get it to boil.
Okay.
And the boiling point increases. That's called delta T sub B.
Delta T sub B.
It's directly proportional to the molality of the solute.
Okay.
And that's represented by the equation.
Yeah.
Delta T sub B equals K sub B times molality, where K sub B is a constant that's specific to the solvent.
Okay.
And as our examples show, we can actually use this relationship to figure out the molar mass of a non-volatile solute simply by measuring how much it raises the boiling point of a known solvent.
Wow.
Pretty cool.
That's handy. Okay, and then we have depression of freezing point.
Yeah, so just like adding a solute raises the boiling point, it also lowers the freezing point of a solvent. Think about what happens when you add salt to an icy road. It lowers the freezing point of the water, and that helps melt the ice.
Smart.
So the decrease in freezing point, that's delta T sub F,
Delta T sub F.
is also directly proportional to the molality of the solute. That's represented by the equation. Delta T sub F equals K sub F times molality, where K sub F is another constant specific to the solvent.
Okay.
And again, just like with boiling point elevation, we can use this relationship to calculate the molar mass of a solvent.
Gotcha.
The sources have some examples showing how to do that, and they even include a table listing K sub F and K sub B values for common solvents.
Very handy. Now, last but not least, we have osmotic pressure.
Osmosis. Okay, so picture this. You have two solutions with different concentrations, and they're separated by a semi-permeable membrane.
Semi-permeable.
So it's a barrier that lets solid molecules pass through, but not the larger solid molecules.
Gotcha.
And what happens is the solvent will naturally flow from the less concentrated solution to the more concentrated one.
Okay.
That's osmosis.
Osmosis.
And osmotic pressure, denoted by the Greek letter pi, is the amount of pressure that you would have to apply to the more concentrated solution to stop that flow, to stop osmosis from happening. Now, for dilute solutions, this osmotic pressure is given by a fairly simple equation. Pi equals CRT, where C is the molarity of the solution, R is the ideal gas constant, and T is the temperature.
Okay.
This is actually a super powerful technique because it's very sensitive. We can use it to determine the molar masses of really large molecules like proteins,
Wow.
because even a small amount of a large solute will create a measurable osmotic pressure.
Okay.
Our sources also talk about isotonic, hypertonic, and hypotonic solutions and how important they are in biology, like what happens to your blood cells when they're in different types of solutions. And they also go over real-world applications of osmosis, like reverse osmosis, which is used to purify water.
So it's all very relevant to everyday life. Now, sometimes when we try to determine the molar mass of a substance using these colligative properties, we get weird results.
Right.
We end up with these things called abnormal molar masses. What's going on there?
So abnormal molar masses, they pop up when the solute either breaks apart into more particles in the solution, what we call dissociation, or when multiple solute molecules clump together and form larger particles, which we call association.
Association. Gotcha.
For example, if you dissolve an ionic compound like potassium chloride, KCl, in water, it actually splits up.
Right.
You get K+ ions and Cl ions.
Makes sense.
So you've essentially doubled the number of particles in the solution.
Right.
That leads to a lower apparent molar mass than you'd expect.
Okay.
On the other hand, you have something like ethanoic acid. In a nonpolar solvent, like benzene, it can actually form dimers, so pairs of molecules.
Okay.
That reduces the number of solute particles, and that gives you a higher apparent molar mass.
So how do we account for these deviations?
Well, that's where the Van Hoff factor comes.